So we can abstract it more generally, as in this diagram here. We have a bunch of machines. Here, I think of bioinformatics machines. Those machines deliver their answers to disks. Those disks are attached to computers. I should say in the traditional cloud architecture, each computer has the disks are actually stored on the physical hardware, so each CPU has its own disk or disks. In a more traditional high-performance computing architecture, you do it differently. You have a storage system, which is either an object store on Amazon or a shared file system like Lustre on in HPC, and so you have all your um, data in one place and all your nodes in another place. But there's still logically some connection between data and nodes. And so that's what these arrows here are showing. The data scattered over the disks is handed to the compute nodes. Then we might have multiple maps, one or more maps. And then finally, we get a reducer operation, which is what the user sees when they drink their drink or see the answer of their web query. This shows a slightly more general structure, which is needed in many cases, which generalizes MapReduce to say that there are many examples of parallel algorithms which don't have this form of map followed by reduce. Rather, they have MapReduce, MapReduce, MapReduce. And those are so-called iterative problems. You can implement those problems with the original MapReduce, but they can be done more efficiently if you know they're iterative, because you can cache the answers in the memory of the machine and not do as traditional MapReduce does, write them out to a disk at the end of each operation. So always there's probably some final reduction to get the actual answer, but internally the parallel computing might have these multiple MapReduce phases. And in fact, we introduced, this is the work of Judy, student, and Judy Chu. We introduced these 4 forms of MapReduce. The simplest is actually map only. There are examples where you do not actually need a reduction operation, but just essentially a map operation. An example could be the program BLAST in bioinformatics, where the map is comparing some gene sequences with a database. Another example could be analysis of the Large Hadron Collider events, when the Large Hadron Collider events come out of the accelerator and then mapped into a different form, where in the different form, the raw data is completely processed. So map only is actually a pretty common feature of many data-intensive problems, because your raw data gets mapped into information, and that mapping of raw data into information is often what we call pleasingly parallel, namely every data point can be mapped independently, and there's no collective operation like reduction. Reduction is noticed as an operation that mixes the input data together. And that's obviously essential for information retrieval, which is shown in type B of MapReduce, where we have to, the user does not want the result of the mapping of the query on each node of the computer. They want a single list. In fact, they would go bonkers if they got multiple lists. So that search engine is like that. Actually, the final step of the Higgs boson analysis is also of this form. The basic in the Large Hadron Collider example, from the raw data to the information is pleasingly parallel. But when I convert the information into histograms, those histograms are combining the results of all those events. So that actually is a very classic reduction operation, because I have to add the results of processing multiple events together, each event processed typically on each set of events processed on a single node. So LHC is actually, although it's typically not done with MapReduce, is architecturally classic MapReduce. Then we get the set we call Iterative MapReduce, where we'll mention that a little later on. In fact, K-means, which is the next lesson group, is of this form. You start off with reading the data. In the case of K-means, it's those points which we wish to cluster. Then we need, if remember what K-means is, K-means is an iterative algorithm. You take the points with a particular set of centers, and you associate the points to the centers, recalculate the centers as centroids, and then you will find that the maps are the association of points to centers, and then the reduction are adding up the contribution of each point to get the centroids. So the final answer of the reduction operation is new centroids, but that is actually iterative because we know that we need to iterate that. In fact, K-means is a good example of iterative MapReduce. And then the final set D is actually possibly the most common up to now example in parallel computing, where you can think of parallel computing of say, I don't know, looking at the evolution of the universe with partial differential equations or particle dynamics. Those have a similar structure with independent processing, which can be called maps. But then the type of communication between the processes is rather different. It's often so-called nearest neighbor, because the local interactions typical of partial differential equation solvers do not have these collectives typically, although they sometimes actually do have global reductions, but most of the communication is often not of that form, but rather so-called local communications between processes holding neighboring points after the decomposition. So if we go to these exascale machines people are planning, they will probably be largely running type D of the MapReduce, and that has some implications for the computer architecture, because type D typically have smaller messages, smaller communications. These tend to be rather big communications here with lots of data. These have lots of small communications, and so you need very high performance communication networks with low latency. So Judy Chu at the Indiana University has generalized this to a map collective model, and she has some MOOC lessons describing this. Here we'll just give a very brief introduction, which you can go and look at this other MOOC to follow up on. And she has generalized MapReduce to map collective, so that you can have not just reduction operation, global summations and things like that, or global sorting on ranks, but arbitrary so-called collective operations. What we mean by collective, or what the world is used, the term collective in this field is used to describe operations which involve all the data, as opposed to, say, the nearest neighbor communications with MPI, which only involve small subsets of the data. And anyway, she has a major research effort looking how to do these collective operations of different types on different internal connections, which are on so-called high-performance computing clusters, are often done with a technology called InfiniBand. If you go to Azure or Amazon commercial public clouds, you will find that you'll get different networks which tend to be lower performance, which is bad typically for things like these MPI style communications, but applies okay to collective operations which are less sensitive to latency. And these are more general ideas of map collective apply for general data, not just key value pairs. So her group has a system called Twister, and Twister has this general structure of compute steps, followed by communication steps, followed by reduce steps, which we said generalized into arbitrary collective. And another difference between iterative MapReduce and Hadoop, this classic MapReduce, is that you only need to transfer the data that changes from iteration to iteration. For example, in the k-means, the points are unchanged from iteration to iteration. So you certainly never need to do any communication with those from between iterations. The things that change are actually a relatively small amount of data, namely the centroids. The only difference between one iteration and the next are the values of the k centroids. And so the only thing that gets transformed, which in the case of k-means is a broadcast, you need to broadcast all the centroids to all processes involved in the computation. Twister runs on Linux when it's called Twister, or it runs on Azure, the Microsoft Cloud, where it's called Twister for Azure. And technically, the Judy Chu's group uses different approaches for those two examples because there's a large amount of research on how to do reduction operations in an optimal fashion, and you will need to look at the details of each platform to decide how to do it best.